Well, thank you very much, Nick, for that kind introduction. It's a real pleasure to come out and give this seminar today. Of all of the topics that I work on, I think ionospheric outflow is by far my favorite. Um, but Today I want to talk to you about some recent work that I've been doing. This is all, stuff that I've done in the past year or two, so a lot of new work. But before I jump into it, I want to take just a moment to acknowledge my co-authors, Gabor Toth at Michigan and Mei-Ching Fok, who I work with at Goddard. And also, I'd like to acknowledge Stan Solomon for making the GLOW model available, which is a very useful tool that I'm going to use in this presentation. So, before we dive into the material, I want to go over briefly what topics I'm gonna cover, and so I'm going to start with description of background and motivation, why you should care about ionospheric outflow and why this is an important topic. So after I hopefully convince you of that, I'll tell you about how you model ionospheric outflow, in particular using my polar wind outflow model and the new developments in there, especially the addition of kinetic ions to the code for global kinetic outflow solution. And then I'm going to talk about how you do this sort of simulation quickly, so you can actually use this global kinetic outflow solution for coupled magnetosphere runs, so you can represent the outflow with a reasonable computational expense. And then I'll maybe spend a little time on results. No, I will go through results, and I'm going to have, I'll try and start on the simple level, so individual outflow along an individual sunlit field line. And then I'll talk about a single field line in the cusp where you have resonant wave particle interactions and soft electron precipitation. Then I'll look at the global solution, combining the convection and the cusp effects. And then finally, I'll talk about consequences for the magnetosphere. And to do that, I'll use the outflow model coupled with the multi-fluid Batts-Rust code and the SIMI model for ring current and radiation belt. So that's the overview. So to start off with, why is this an important problem? Well, ionospheric outflows have been studied for a very long time. Some of the earliest papers predicting a polar wind type of supersonic outflow from the polar region of protons was predicted in the late 60s and experimentally confirmed shortly afterwards. Now, since those early observations, ionospheric outflows of not just protons, but also oxygen, helium, even nitrogen in some cases, and other species have been observed very frequently on a number of missions. But even though we know that it's happening, there's still a lot we don't know about how it's driven and what consequences it has. So one of the consequences that ionospheric outflow has goes to the question of what's the origin of near-Earth plasma. And so if you think about it, all the plasma that's in the magnetosphere derives from one of two sources. Either it comes from the solar wind or it comes from the ionosphere. And so a nice way to visualize that, I borrowed this from a paper from Robert Wingley, is to think of the concept of the geopause, which is a boundary inside of which the plasma is largely of ionospheric origin and outside of which it's mostly from the solar wind. So these are from some multi-fluid simulations. And what you can see in these simulations is that the region controlled by ionospheric plasma potentially is quite large, and it varies a lot with the solar wind conditions. But the ionospheric outflow isn't just protons, it also includes other species, and in particular, there's a lot of interest in oxygen. And the reason for that is while protons can come from either the solar wind or the ionosphere, if you see oxygen in the magnetosphere, it really can only come from an ionospheric source. So these are from some of the first observations of that. So this is from a paper by Shelley et al. 1972. And these were the first measurements of O+ of ring current energies raining down into the magnetosphere. I don't want to spend a lot of time on it, but for this particular event, um, they found that not only do you have a lot of ionospheric plasma in the magnetosphere, but they estimated that it would be about 4 times the energy density carried by the O plus compared to the H plus. So the ionospheric plasma is getting out there, and it's important for the energy balance. And that's not an isolated event, so this is a nice result from Nose et al. Combining a lot of different studies, and they're showing the contribution of O plus to the energy density of the ring current as a function of the strength of the ring current as measured by DST. And what you see here is basically for stronger events, the more O plus or the more ionospheric plasma is contributing to the ring current energy density. So if you're interested in understanding the magnetosphere during strong geomagnetic storms, you really want to understand where the plasma is coming from, and you need to understand how it's getting out of the ionosphere. So I hope by this point I've convinced you that you should care about ionospheric outflow. So the next question is, how do you represent ionospheric outflow? If you want to do a global model of the magnetosphere, how do you represent this source? So there's, basically I think 2 approaches to this. Either you can use an empirical model for the ionospheric outflow, or you can use a first principles model. And in the empirical model, I think you can think of it as, you have to set the density and velocity either to an average condition, or in a more sophisticated way, using tying the energy inputs from the magnetosphere in order to dynamically adjust the boundary condition. And so a very popular way to do this is to use this famous relationship from Bob Strangeway that relates the Poynting flux and the electron precipitation to the outflow. And so that approach has a lot of advantages. Conceptually, it's a lot of work, I'm sure, to implement, but conceptually it's straightforward and it's very clear what you're doing, and the outflow is driven by energy inputs from the magnetosphere. On the other hand, the downside of this approach is that you don't have physics in terms of what mechanisms are ultimately driving the outflow, and so for that you really want to go to a first principles model. So in that approach, you construct a global model of the ionospheric outflow, and you use that to set the inner boundary condition for your magnetosphere simulation. So that approach has the advantage that you have a lot of physics in it, has the disadvantage that it's more computationally expensive, and your model is only as good as what physics goes into it. So if you're missing some key process, your representation might not be that good. But nevertheless, this is the approach that I'm going to talk about for the remainder of this talk. So the model that I'm using is the polar wind outflow model that I've been working on for a number of years now. And the basic idea is that you're solving the transport of plasma from the ionosphere to the magnetosphere with along a single expanding magnetic flux tube. So you imagine that the lower boundary of your flux tube is below the F2 peak, and the upper boundary is in the magnetosphere, and you solve for the transport along there. By using multiple convecting field lines, you're able to reconstruct the whole 3D solution. So this is an example of that shown in this figure, which unfortunately doesn't project very clearly, but you get the idea, I think. But I want to focus this talk really on what's new. I don't want to spend a lot of time talking about things I've talked about in the past, so I want to focus on the new features of PWOM. And so one is I've included new treatments of the superthermal electron population. These are the photoelectrons, auroral precipitation, secondary electrons. I've expanded the model to go to a kinetic ion description using a MAC, sometimes called a MAC-PIC approach. It's basically a hybrid PIC type of solution with Monte Carlo collisions. And I've expanded the model to work for other planetary environments, Jupiter, exoplanets, and Saturn. I'm not going to talk about this last point. I'm going to spend most of the time talking about these first 2 features. In particular, I want to talk about the second one, because this was, I think, the most work. So I think you can start with the question of why do you want to include a kinetic ion description in your model of ionospheric outflow? What's the point? And to answer that, it actually goes back to a very old controversy. So if you go back and read through the literature of the early papers on ionospheric outflow, the earliest models of polar wind were hydrodynamic models, and they were criticized basically immediately. People were especially questioning the validity of the hydrodynamic approach. So they were saying, well, you can't explain the neutral exosphere with a hydrodynamic model, so why should it work for the polar wind? I think a very nice paper by Marabushi in 1970, did very detailed comparison of steady state hydrodynamic and kinetic models. And they found that while you can get very similar answers if you look at just the fluxes, if you look term by term, you find out that you're overestimating the effect of collisions in the hydrodynamic model. There's other issues too. For example, you can have very non-Maxwellian distributions in the outflowing solution, where you can diverge, quite a bit from a Maxwellian. And this can happen in a number of ways. And one way that you can get non-Maxwellian distribution is the effect of wave-particle interactions, ion cyclotron resonant heating and the like, giving you ion conic distributions. And it's very hard to include these effects into a hydrodynamic model. So, really, there's a lot of good reasons to consider extending beyond the hydrodynamic approach for this problem.
A point of clarification on that slide.
Yeah.
Do you mean horizontal speed or perpendicular to magnetic field? Horizontal might just be, horizontal.
Oh, no. This is in the frame of the moving with the field.
Okay.
Yeah. So the perpendicular velocity is perpendicular in the plasma frame.
Okay.
Yeah. No, that's a very good question. But despite the fact that there's very good reason to go beyond the hydrodynamic approach, you don't want to throw it away because there are a lot of advantages. It's much easier to include chemistry in the hydrodynamic approach. It's much easier to deal with very collisional environments. So you want to identify what's the region where this is really valid and use that model there, and only put the transition, to deal with the region where the hydrodynamic model is not a good description. So, one way you can estimate that is to go back and think about what are the regions of outflow. At the base of the field line, you're dominated by chemistry and collisions. And then, eventually you'll go through a transition region, you'll become completely collisionless. But there are a couple of important altitudes in here. So one is the neutral exobase, where the ion-neutral collisions become no longer important. And there's also the ion exobase, which a lot of people don't think about, but this is where the ion-ion collisions stop becoming important. And you can estimate the height of the ion exobase by looking at where the Knudsen number is equal to 1. Or where the mean free path of the collision is equal to the scale height. So if you do that in the model, you find that that transition happens, around 2,000 kilometers, and that's an estimate that's consistent with some previous studies. So if you're looking at, what's an appropriate description, really anywhere below the ion exobase, the hydrodynamic model is probably valid. And as you go above the ion exobase, you're basically losing validity if you're using the hydrodynamic approach. On the other hand, the kinetic model is valid everywhere. But as you go down to the very collision-dominated and chemistry-dominated regime, the kinetic model gets very, very expensive. And, so what we want to do is to take the best of both worlds. And so that's why now we've gone to a new description for PWOM. So this is a combined fluid and kinetic description of the model. So what we do is we use the hydrodynamic model at low altitudes, and we transition to a kinetic hybrid PIC description at high altitudes. And then we couple back and forth in order to make these models run together seamlessly. And you put that transition in the region where both approaches are valid descriptions of the plasma. Now, we also include the superthermal electrons. I'll talk more about that later, but basically in the work I'm going to show today, I'm using the two-stream glow model, feeding into a collisionless kinetic description, a LUVO mapping at higher altitudes. And then the electric field is described by a generalized Ohm's law. Now, this is basically a new model capability that lets you study global kinetic outflow, um, which I think is quite nice. So this is not entirely a new idea. This is actually very similar to the model of Jim Horowitz's DIFK model, or the GP. It has some similarities also with the GPW model developed at Utah State University. But I think, as you'll see, that there's some very nice advantages with this implementation. So what I want to do now, I really want to step through each of these pieces in more detail, so you can really understand what I'm doing with the model. I don't want there to be a mystery. So let's start with the fluid and ion kinetic descriptions. So like I said, we're using the hydrodynamic model at low altitudes and the hybrid PIC model at high altitudes. So what goes into the hydrodynamic solution? Well, basically, this is the same thing that I've been doing for many years with PWOM. So I'm solving 5-moment gyrotropic multi-fluid description plus heat flux along a flux tube. I do this for multiple ion species. So in the case of Earth, I'm doing it for O+, H+, helium+. And the chemistry and photoionization source terms are all included here. And also we include the ion-ion, ion-neutral collisions. Also ion-electron collisions, but I forgot to write that. So what goes into the kinetic solution? Well, this is a hybrid PIC type of approach, but since we're in a very strong magnetic field limit, we're using the gyro-averaged particle equation of motion. And we're pushing particles with a fourth-order Runge-Kutta scheme. For every fluid population in the hydrodynamic model, we have paired a particle population for the kinetic model, so they match up, 1-to-1. It's very important that you include collisions in this because, you have to do this transition in the collisional regime. So I include the ion-ion nonlinear collisions using the algorithm. This is a very well-known algorithm described by Takazuka and Abe. And so that's included. And one nice feature of going to the kinetic description is you can now include resonant wave-particle interactions in the model. This is hard to do with a hydrodynamic approach without going to higher moment, and even then it has some issues. But when you're solving with a hybrid PIC description, including wave-particle interactions is very straightforward. And so I'm using an approach described by Barakat and Barghouti, and actually the earlier papers by Crew and Juan Redder that describe how to do this as well. And also to control my statistics, because we're covering a very wide dynamic range where you have very high densities at low altitudes and very low densities at high altitudes. So the statistical weighting of the particles is variable, and I'm using a technique of particle splitting and joining where I can clump together particles or split particles apart in order to try and maintain reasonable statistics. So sometimes this is called particle rezoning, and I'm doing this using an approach described by LaPenta for his PIC code, but a very similar approach works here as well. So, a very critical aspect of this is how do you handle the interface between the hydrodynamic model and the kinetic model? And so here I want to zoom in on that interface and explain that in a little more detail. So the basic idea is that from the top cell of the top computational cell of the hydrodynamic model, we can get the ion moments, the density, velocity, temperature for every ion species. And from that, you can sample particles randomly from a Maxwellian. And so then those particles are injected down into the bottom boundary cell of the kinetic description. Now, of course, we have to feed back. So the first computational cell of the kinetic description, we accumulate particles in that cell, and then we can compute moments for all the ion species. And then those moments then go back to populate the top boundary cell for the hydrodynamic model. And so in doing this, we can handle this trade-off very nicely.
Do you iterate?
There's no, because it's time dependent, we just do this every time advance. So there's no back and forth iteration. But it's iterating in time. You're constantly providing new boundary and providing updated Yeah, but if it was a steady state calculation, you would definitely iterate this back and forth. But in this case, there's no iteration.
And this is, so are you doing this for every time step of kinetic and fluid, or is there like some exchange time where they only exchange information intermediate?
No, that's a great question. So if you want to do this for every time step of the model, the hydrodynamic model's time step is controlled, actually down in the collisional region, which is very, very, very short time steps. So it turns out that, but for the kinetic model, your time step is controlled by the collision time between, among other things, but, controlled by the collision time between particles, the mean time between collisions, which is much longer. So if you did it every time step, it would actually be extremely onerous. So what we do is we do it on a cadence, and it's an adjustable cadence. So what I did is I say, okay, let's do this every 1 second. But then I varied that. So one of the studies that I did is to make that every 0.1 seconds and make it every 10 seconds, and then see, what's an ideal choice. And it turns out 1 second works about right. All right, so the other issue with the interface is you have to know where to put it. And just like with real estate, it's location, location, location. Where you put this is quite important. So in principle, this interface can be anywhere below the ion exobase, and that would be fine. But the problem, of course, is if you put it too low, then the kinetic model becomes very, very, very slow. So you want to put it below the ion exobase, but not so low that you slow down the kinetic calculation. So I put this somewhere between the ion and neutral exobase, which is about 1,000 kilometers. But again, that's an adjustable parameter. It can go anywhere. So, as I pointed out a couple of times, including collisions in the kinetic model is very, very important if you want to handle this nice two-way exchange between those model descriptions. So I think it's very useful to verify that collision operator is implemented correctly. So I just want to show you one example of model verification that I've done with this code. And so this is a very standard test problem. It's the equilibration of temperature. And the basic idea is that you initialize a cell with two populations. You have a very hot population and a very cold population. You put them together, and then you let them keep colliding. And over time, through the collisions, the hot population is going to get colder, and the cool population is going to get warmer until they come to an equilibrium, and the temperature difference between those two is going to go to zero. So there's a lot of good reasons for why this is a good verification problem. So it's easy to understand, but more importantly, there's an analytical theory, an analytical solution to the problem that you can compare against. And that analytical solution is only valid in the short time regime when both populations can be described as roughly Maxwellian. But in the long time regime, there's a lot of previously published work that you can compare against directly. So you can compare both the long and the short time and be sure that you're implementing things correctly. So another reason that I wanted to do this type of verification is because unlike previous models for using this approach, I decided to implement variably weighted particles, where every particle can have a different statistical weight. Now, that's great, but the algorithms originally developed for equally weighted particles, so I want to verify that I'm accounting for the variable weights correctly. So to do that, I'm considering two cases, the hot and cold population with equal weighted particles and the hot and cold population with variably weighted particles. So I can test a lot of things with this verification. And so this is the result. So what I'm looking at here, so this is the normalized temperature difference on the y-axis and the normalized time on the x-axis. And the first thing that you can see is that it doesn't matter if you use equally weighted or variably weighted particles, you'll get essentially the same result. So that's good. It's implemented correctly for variably weighted particles. The other thing you can see is that in the short time frame, you agree with the theory, which is what you expect. Now, in the long time frame, where the theory is no longer no longer accurate, you can compare against previously published results. So this is from a paper by Ron Miller and Mike Comby in 1994, and you can see that you basically recover their solution. So this gives me a lot of confidence that this is implemented correctly. And in developing the code, we do a lot of these types of tests, but for collisions, it's particularly important. So that's enough about the ions for now. So I want to talk very briefly about the superthermal electron treatment in the model. So, there are a lot of mechanisms by which the superthermal electrons can affect the outflow. Well, a lot. There's two mechanisms by which they affect the outflow, but maybe two is a lot. So one is basically the electrons are very light and flowing out, and so you get a parallel electric field or an ambipolar electric field that forms between the electrons and ions and helps to counter gravity. You also have collisional coupling, so superthermal electrons colliding through elastic collisions with the thermal population, depositing energy to them and heating the electron gas. So in PWOM, we include this effect in a pretty simple way. So we basically split the electron population into two populations. We have a thermal population and a superthermal population, and they have to satisfy some pretty straightforward relationships. So basically the sum of the thermal and superthermal population have to equal the sum of the ions. That's just a statement of quasi-neutrality. The sum of the thermal electron flux and the superthermal flux has to equal the sum of the ion flux with whatever current is flowing into the system. Excuse me, that's just a statement of current conservation. And then for the thermal electrons, we solve an energy equation where we also have to then keep track of the energy deposition from the superthermal population. So that's all relatively straightforward, but it's all predicated on having a solution for the superthermals. So where do we get those from? Well, we get them from three choices. So the first choice is the simplest. So you take an external calculation for the superthermal flux and impose that on the model together with a collisionless kinetic mapping, and that gives you, one approach. Excuse me, losing my voice a little. Now the other approach in the next level of complexity is to use the two-stream model. So in this case, I'm using a GLOW model from Stan Solomon based on the two-stream approach of Banks and Nagy. And so in this approach, you represent the sources of the electrons and the transport of the electrons, but it's kind of a hybrid between a full kinetic solution, which is not quite that, but it's also better than the externally imposed. And then there's the fully kinetic description of the electrons. In this case, I'm using the STEP model from George Kozanov and Mike Lamone. And I just published, actually, a few months ago, it came out in JGR, the coupling of this model with PWOM. But in this talk, I want to actually use the second one, because while the fully kinetic solution is undoubtedly correct and is really fantastic code, it's very computationally expensive, and I want to be able to do this problem quickly. And so, in my view, the two-stream approach is kind of the ideal blend between including the right physics and running fast enough to get something done. And so that's the approach I'm going to use in this presentation. So, speaking of speed, we want to speed up the calculation. We want to be able to have this code be able to run inside of a global model framework. And so to do that, we have to make things go quickly. So what we do is we use a combination of distributed and shared memory parallelization to make this go fast. So each individual field line is run on a separate processor. So we're using shared memory decomposition, shared memory parallelization distributed memory parallelization for the field lines. So each field line goes on a separate MPI process. And then within each MPI process, we have a bunch of particles. And so we want to speed up all the particle work using shared memory. So we use OpenMP for that. So we kind of have two layers of parallelization going on in order to speed up the code. And I'm not going to talk a lot about the performance, but we did do scaling studies. And basically, if you use 5 OpenMP threads per MPI process, you can match your hydrodynamic performance. And what that means is that you can do global kinetic outflow solutions, and while they're still expensive, they're achievable. So you pay a penalty of about a factor of 5 in terms of computational requirements, but that's still within the realm of what's available on existing supercomputing machines. So that's, a long description of the model, but this is where a lot of the fun was from my point of view. So I just summarized this before moving on. So we've expanded PWOM to go to a combined fluid and kinetic approach with fluid description at low altitude, hybrid PIC at high altitude. The modeling approach includes the collisions, the hot electron population, wave-particle interactions, and multiple layers of parallelization for fast execution. And so that's the approach we're using, and so now let's use it. So here's some results. So just to remind you, we're going to step through these in levels of complexity. So we'll start with the simplest case at the top and the most complex case at the bottom. So for the simplest case, we're talking about the sunlit polar field line with nothing else going on, just sunlight shining on the atmosphere. Then we'll go to the cusp, then the global cusp with convection, and then the coupled model with the magnetosphere. So this is the sunlit polar field line solution. So this is altitude profile of density on the left, and an altitude profile of velocity on the right. The solution for O plus and H plus is shown. And I decided it would be interesting to compare the hydrodynamic solution and the kinetic solution and see just how similar or different they are. And if you're looking at the hydrogen, actually, the protons, they're not that different. The density profile for the protons is very similar, and the velocity profile is also very, very similar between the two. And so actually, if you're only interested in classic polar wind proton outflow, you get a very similar solution with the hydrodynamic approach. For the oxygen, the velocity looks very similar. Basically, if you only have photoelectrons, the oxygen doesn't move very much. The density structure is a little bit different, though. They're both very similar below 2,000 kilometers, but as you go above 2,000 kilometers, the kinetic solution drops off faster than the hydrodynamic solution. So I thought that was kind of interesting. But a much more interesting case from my point of view is the cusp simulations. So, above the cusp, outflow driven in the cusp region has a lot of things going on. You have precipitation and you have wave-particle interactions. And so I want to talk about the wave-particle interactions first. So frequently above the cusp in the aurora, if you look back at Dynamics Explorer observations, for example, you see this turbulent wave spectra above those regions, with the power concentrated below the O plus gyro frequency. So one of the ideas, actually several ideas for wave-particle interactions, but one very popular one is the so-called ion cyclotron resonance, where a particle is gyrating around the magnetic field will interact resonantly with a portion of this turbulent wave spectrum, and it will heat perpendicularly. Now, this excess perpendicular heating gets converted into organized parallel motion via the mirror force. And so what happens then is that the particle heats up perpendicularly, and then it starts to accelerate parallelly. But it doesn't happen to the whole distribution at once. The mirror force is stronger for higher perpendicular velocity. And so the edges of the distribution start to accelerate up first, and then the core lags behind, and that carves out kind of a V shape in velocity space. So that V shape looks kind of like a cone, and hence the term conic. So this is now something that we can do in the model. Before we couldn't do this with the hydrodynamic description, but with the new kinetic description, we can do this. And so what I did is I consider a single, excuse me, I consider a single cusp field line exposed to soft electron precipitation and wave-particle interactions. And you can see that when you do this, I guess the text's a little bit small, but this is the O plus velocity, which was stationary when you only had photoelectrons, but is now growing to around 15 kilometers per second at the highest altitudes. The O plus density, which had a crossover altitude around 3,500 or 4,000 kilometers when you only have photoionization, now actually it reaches almost the very top of the model. So the O plus becomes able to reach very high altitudes. But we don't just have to look at the moments. We can also look at the evolution of the velocity space distribution function. And so here, these are different altitude slices of V perp and V parallel. And you can see that you're getting heated perpendicularly. And by the time you reach around 4,000 kilometers, you have a very nicely formed conic in the model. But, so that's very nice. But, the field line's not just stuck in the cusp and held there. These field lines are moving around the polar cap, and they're moving into the cusp and out of the cusp. And so you really want to look at this using multiple field lines and look at them moving through the polar cap. So yeah, Mary.
Can I just ask, what are you assuming is doing the perpendicular?
Yeah.
Ion cyclotron waves up there.
That's exactly what we're assuming. And so one drawback of this approach is we can't solve for the waves themselves. So we have to impose a wave spectrum. We impose a spectral index and excuse me. Seem to be losing my voice. Very bad timing.
And that's tied somehow to the turbulent current or something like that.
So in this case, we're just imposing it based on observation. So there's some observations that say this is a typical value that you can use above the cusp. And so we're just putting that in. The actual source of the waves is not well known. There's a number of theories. There's some theories that could be driven by the parallel current. There's also theories, from Ganguly, Guru Ganguly, showing that velocity shear, for example, could give you these waves. Yeah.
So when
While you're asking, I'm going to grab some water. Sorry.
Good timing.
Go ahead.
When you're including this wave particle interaction, how do you decide the altitudinal dependence of the spectra and all these perpendicular heating things?
No, that's a very good question. So there's a paper that looks at exactly that by Crew, and basically they're assuming that the wave spectrum is constant with altitude. There's a paper by Gurnett that shows that might be true. And then basically, as you're moving through different regions of magnetic field, your cyclotron frequency is changing, and so the portion of the spectrum that you're interacting with is changing, and that's giving you a different quasi-linear diffusion coefficient. And so that's the basic idea. Does that answer your question?
Yeah.
All right. So actually, I would just say that I think what to use for the waves is the biggest source of uncertainty in this approach. But nevertheless, we press on, and so to test what this cusp effects look like when you include convection, I impose a typical two-cell convection pattern, on the polar cap. And I also artificially impose a cusp region. And in that cusp region, I put a soft electron precipitation. I turn on this wave heating term. And what you can see is that connected to the cusp, these either two different altitudes. So connected to the cusp, you have elevated O plus flux and elevated H plus flux. And the percent of O plus at high altitudes is much more pronounced in regions connected to the cusp. And actually, some of that higher O plus ends up dragging across the polar cap. So you're heated on the day side, and then it's being dragged across the polar region. Now, one thing that kind of surprised me with this is while both the O plus and H plus flux are enhanced associated with the cusp, if you look very closely, you see that they're actually displaced from each other. That the H plus flux is enhanced, but it's more past the cusp, more poleward of the cusp. And that kind of puzzled me for a while, but I think I have an explanation for it. And the idea is that the soft electron precipitation that's giving you enhanced density in the cusp region is mostly creating O+. Um, and then the H plus is largely being created by the accidentally resonant charge exchange, H plus O giving you H plus O plus. This goes two ways. So I think what's happening is you're producing enhanced O plus at low altitudes in the cusp, and you're dragging that O plus poleward. But then there's a chemical lifetime, where you're producing your enhanced H plus. And so the H plus cusp ends up being displaced from the O plus enhancement ends up being displaced from the H plus enhancement because of this interplay between chemical lifetime and convection time. So I'm not 100% sold on that explanation yet, but I think it kind of makes sense. So
if your kinetic part also includes chemical reactions or only the hydrodynamic?
Only the hydrodynamic part. So most of the chemistry is happening below 500 kilometers, and the kinetic model starts around 1,000.
So what time it takes? Because you're looking at 4,000 and 6,000 kilometers. So those must be transported from low altitude.
That's right. That's right. So yeah, so I mean, you can evaluate. I didn't do it here, but you could evaluate those times, absolutely. But definitely that conversion from one species to the other happens in the hydrodynamic portion of the code, but then the acceleration happens at higher altitude. Yeah.
Could the velocity filter mass spectrometer effect be applied here? If the hydrogen H plus is moving along the field line faster, it's going to get to higher altitude, while convecting. So at 4,000 kilometers, you might see it being further poleward than the oxygen, which is stuck lower down still. If you see what I mean?
Yeah.
That.
I do see, but in that case, if the H plus is transported faster along the field line, I would expect to see it faster, closer to the cusp, but I see the O plus actually closer to the cusp. So, I mean, it's a good idea, but I'm not sure that works.
Right.
All right. So, the very last thing I want to talk about is kind of where I started with. At the very beginning of this presentation, I was talking about why you care about the outflow, but I was mostly talking about the magnetosphere, that it's important for the magnetosphere. So I want to end with coming back to the magnetosphere. So how do you put this type of kinetic outflow model into, a magnetosphere model? And so actually, the nice part is this part was already solved. So in 2009, I expanded BATS-RS to be multi-fluid model, and I, together with my co-authors, and I, put PWOM into BATS-RS, so I can use the polar wind outflow model to set the inner boundary of the multi-fluid BATS-RS code. But I want to see also the impact on the ring current, and so in 2013, I worked together with Mei Ching, Falk, and others to put CRCM, which is now evolved into SIMI. That's a whole nother discussion, but basically to incorporate a two-way coupling between the ring current population and the magnetosphere population. And so this was already done in 2013. This coupling was already done in 2009. And none of the things that I did here actually affect any of those couplings. The only thing I had to do was to generalize this coupling a little bit to account for multiple ion populations being passed between the inner magnetosphere model and the global magnetosphere model. And so, you can just immediately start using this this new capability. And so that's what I want to show you now. So this is the first test that I did with this new capability, putting the outflow into the global magnetosphere. So this is a pretty simple test. Basically, I'm using constant solar wind conditions where the fixed density of 5 particles per cubic centimeter, 400 kilometers per second, and magnetic field IMF, just constant southward, -5 nanotesla. And so, one of the problems, we mentioned this before, but actually this is true all the time. The biggest uncertainty is the waves. Where do you turn on the wave particle interactions? And so there are a couple ways that you could go about this. You could maybe consider using pointing flux. I don't like that though because the pointing flux is alphanic and this is cyclotron. So I'm not sure that they should be connected. But you can kind of go with a semi-empirical approach for where to turn on the wave-particle interactions, because many people, when they look at Bob Strangeway's paper, they see the correlation between outflow and pointing flux and outflow and soft electron precipitation, but they don't pay attention actually in that paper to the fact that the wave particle or the pointing flux is well correlated actually with the precipitation. So in this case, I decided to take advantage of that, and I used the precipitation coming from Bats R Us to turn on the wave-particle interaction. So everywhere I have precipitation exceeding some threshold, I turn on the empirical specification of the wave-particle interactions, and when I'm outside of that threshold, I turn it off. So
Could you clarify that a little bit?
Yeah.
So what in Bats R Us specifies soft precipitation?
Nothing.
That's the precipitation
Yes.
that matters here.
Nothing is the answer. So in Bats R Us, all the precipitation is hard precipitation. And that's something that in order to address properly, the precipitation model has to be expanded. So actually, I have great admiration with what you guys were doing with LFM. I think you guys are, really doing fantastic to include these other types of precipitation. And I think for this type of outflow modeling, that's the direction that all the global models should be moving in. So this is what it looks like. So I've run the model for 4 hours and change, and you end up getting this outflow this is the percent of O plus is what the color bar is showing, and then the magnetic field lines on top of that. And it's a little hard to see with this resolution on the projector, but basically the O plus is filling the lobes, and it's landing actually right near the reconnection site in the tail. And what you see, if the resolution was a little bit better, is that you can kind of see it here though, that the X line is moving around, that you end up getting a lot of plasmoid formation, and the tail stability is really disrupted by this outflow. Now, if you want to take a look at what the outflow that's feeding into this looks like, it looks like this. So this is the O plus and the H plus solution density, velocity, and flux. And then this is the ionosphere electrodynamics output from the code. And so there are a couple of features that stand out. So one is that the density ends up being skewed by the convection. So that's more or less straightforward. So you see the convection has a skew like this, and that ends up skewing the density in the polar region. If you look at the velocity, the H plus velocity really looks kind of like what you'd see just for classical polar wind, but the O plus velocity is very strongly following the auroral oval. And this makes sense because we're basically turning on the wave heating terms where we have auroral precipitation, and so that also makes sense. But one interesting thing, I think the most interesting part, is that most of the flux is coming out on the day side, not on the night side. And even though, for O+, even though you have this outflow going all around the auroral oval, most of that flux comes out on the day side. And, if you think about that a little bit, it makes some sense. While the wave-particle interactions can accelerate the plasma and they can give you velocity, you're ultimately limited by your production of ions. You can't accelerate plasma that's not being created. So on the night side, your sources of ionization are pretty limited. We only have hard precipitation for the aurora, and so all that ionization happens very low down in the E region. And the photoionization on the night side is very small. It's all from starlight and resonantly scattered light from the geocorona. So, but comparatively on the day side, you have a lot of photo production. And so basically what this says is that even though the wave particle interactions give you strong velocity everywhere along the auroral oval, you only get the strong flux coming out on the day side. And if you think about this just a little bit more, I think this has some implications for people who are trying to use empirical relationships to drive outflow. You know, the empirical relationship from Strangeway is very useful, but it's developed entirely for the cusp, which is entirely for one event. So it's only one condition of illumination. And the characteristics of illumination in other parts of the polar region and in the auroral zone are very different from the cusp. And the characteristics of the precipitation are very different. And so I think probably what it means is if we want to use empirical specifications, there's some work we should do to extend these correlations to other regions and to consider a wider range of solar inputs and precipitation conditions. So that's just an observation I think that I came to when looking at these results. So finally, you know, I want to say, well, what's the impact for the ring current? So this is very steady outflow conditions, you know, very steady driving. So not a lot is going on in the solar wind. And what we see is, so this is the H plus pressure in the ring current. So the sun is to the right. And this is the O plus pressure. So this is from SIMI. SIMI is a bounce averaged kinetic model for the ring current. And you have to be careful. The color scales are not the same. So the peak pressure of the O plus is about 10 times less than the peak pressure of the H plus. So for this condition, we do get significant O plus in the ring current, but it's only carrying about 10% of the pressure. And so that's nice. I do want to show one thing. This isn't actually connected to anything else in the talk, but very recently we added a cool calculation, so I wanted to share. And that's we added the ability to calculate L star in SIMI using the Batsar-Rust field. So one of the outputs now is we can look at the third adiabatic invariant drift path for radiation belts. So that's just kind of a new feature that it's not connected, but you know, I thought it was cool. So I can talk to you about it later if you. Oh, go ahead.
Or is that on CCNC?
No, but it will be. It will be. And so the last result I want to show is the 3D view of the outflow. And actually, I mostly wanted to show this because I like the visualization. But there is actually a science point to it, but the visualization was fun. And so basically, it's just showing you at one particular time in the simulation how the outflow is largely coming, at least in this cut, from the cusp region. But you can actually see that outflow is being dragged across the polar cap. And so just because you're accelerated down here, when you see outflow up here, you have to always remember the transport time, that the convection speed is going to transport this accelerated plasma, you know, across the polar region. So that's obvious, but I thought it was a nice visualization for it. So that's all I wanted to say. So this is the summary. You know, we've expanded PWOM to include treatment of most of the major outflow mechanisms. There's still unknowns, you know, related to the wave particle interactions, but if we have better specifications, we can plug those in. We've expanded PWOM to go to a kinetic ion description above 1,000 kilometers, including those wave terms. The parallelization means that you can actually do these types of simulations with reasonable computational expense. It's still expensive, but you can do it. And that's it. So if there are any questions, I'm happy to answer them, or I'm going to be around all afternoon also. I'm happy to meet with people. So.